Hello friends, today once again we are going to talk something on welding, and as you see here in this chart or in the slide, we will be talking about the type of joints and how we want to fill up these different joints, and to make that easy, how code has given us opportunity to classify based on the filler number, or as we discussed earlier, based on the resultant weld metal composition, which is nothing but a number, which we'll be seeing it in the next slide. So first let us understand what are all the different joints. As you see here on these slides, there are four types which I have classified. You can classify more and do detailing of these joints for ease of our understanding, and also the type of joints we use on our regular equipments, parts, assemblies. Those are required to be detailed out in much more. As we go further, we'll see in the third and the fourth slide how it will be seen. So there are butt joints, the square butt joint, which is the simple, where there is no edge preparation. You just cut the plate right angles to the surface and bring it together with whatever the specification, that means either a zero gap or with some gap, and then with backup or without backup. So accordingly you make a joint. Then if the thicknesses are more, normally square butt is used up to 2 millimeters or 5 millimeters depending upon the process. For a TIG welding or for a SMW welding, 2 millimeter to 3 millimeter is what something you can penetrate very well and achieve a good penetration on the other side of the weld. But if you have processes like plasma or activated TIG, concentrated TIG, or very high end processes like laser and EB welding, you can penetrate even square but much higher thicknesses, going from 5 millimeters to 10 millimeters. And if you have really a super high kilowatt rating of your EB welders, then you can go to 70-80 millimeter thickness also. But if that kind of a processes are not practically possible, expensive, or not available, we can switch over to a V joint, Z joint, U joint, single V, double V, or single Z, double Z. And then whether it is equal or unequal thickness which you are getting joined, or equal or unequal in the distribution of the groove on either side of the weld. What is the included angle? We normally recommend 60 degree, that is 30 degree on each plate, but there are joints which will be saying it where on one side there is no possibility of giving a edge preparation, so the entire angle is adjusted for accessibility on one side of the plate, and accordingly the weld edge is prepared on one side or both sides, equal or unequal. And the most important is that after we select the type of joint, then we decide the micro details of this, like root face, root gap, for getting different levels of penetration. And if there are partial penetrations, we can compromise on these root gap, root face, included angle, and other details. Similarly, we can talk of the fillet joint, single-sided, double-sided, single run, multi-run, equal, unequal length, on similar material, dissimilar materials, what is our electrode war or the process what we are using, the positions in which the butt joints and the fillet joints are being done. The third level of the joint is the overlay or the cladding or the buttering, where on a piece of plate we will be depositing different layers, different passes, and then we will be achieving either corrosion resistance, or we will be achieving hard facing, very hard surfaces, or there are sometimes some directional strengths are required, especially in the Z direction, to avoid lamellar tearing. We do buttering, or there are sometimes reclamation built up is required on a worn out part or a wrongly cut part to restore the geometrical tolerances. So buttering is employed. And then we also have a spot weld or a tack weld or a plug weld, or there are tube to tube sheet weld. So there are many types of joints which we can classify and use it. So we must list out for our job or for our type of product or the normally preferred joints or normally used joints in our manufacturing areas, and classify them to the extent possible, make a table, recommend for different materials, for different processes, for different thicknesses, for different positions, all the variables a welder is going to be concerned about, and also on depending upon the filler metal, parent metal, and the resultant chemistry. So to get a feel of the consumables and the resultant chemistry, let's go to the next slide. Based on this joint types and the selection of the consumables, we will be deciding the number of passes and how to lay them and what care is required to be taken. So let's move to the next slide now. In this slide you see that we will be talking about the F number. Typically the F number is the classification of alloys, as you see here. One is for carbon steel, carbon manganese steel. If you go to let's say 7, it is the chrome steel 400 series, that is ferritic martensitic series. If you go to 11, it is the high strength low alloy steels. Or if you go to 21, it is for the aluminium. If you go to 40 series, then it is for nickel based alloys. If you go to 50 series, it is for titanium. 60 series is for the zirconium. So like that, different series and different 1, 2, 3, 4 numbers or ABCD classifications, as many types based on their melting characteristics, melting temperature, the various effects which are listed here on the viscosity, on surface tension, on the inclusions, on the solidification pattern of this, we classify into the F numbers. And as you see here, we have a P numbers which we use it for the parent metal, F number for the welding consumables, but the A numbers are used for the resultant alloy. That means this solid line here and the dotted line, which is the initial edge preparation, this is the distance or this is the thickness, the penetration is going to melt the parent metal, which has a particular chemistry. The F number comes from the consumable, which has another chemistry or maybe a same chemistry, and depending upon the dilution. So for example, let's say that both ends we have a dilution factor of 10%. That means the resultant weld metal is going to be 80% of the filler wire or the ferrite metal or the electrode composition, and 20% of the resultant weld metal or the A number is going to be from the parent metal composition. So for ease of understanding, let's say we have a carbon percentage of 0.1 in our parent metal, or rather in the filler wire, and 0.2 into the parent metal. So now we are going to have 10% on each side in the resultant metal. So 0.2 of the parent metal, 20% of that. That means it is going to be 0.04. What is going to come from the parent metal, and 80% of 0.1. So that is 0.8. So that means 0.8 plus 0.04. So we are going to have 0.84 as our 0.084 as the composition of our. I'm making a mistake. I think let's do it again. What I said is 0.2% carbon and 0.1% carbon. So when 0.2% is going to be on the parent metal and 20% of the weld metal is going to be coming from parent metal of 0.2. So 0.2 into 20%. So that brings us 0.04. And the electrode is going to be 0.1, so 80% of that, so it is going to be 0.8, and 0.8 plus 0.4, so it is 0.12. 0.08 and 0.04 add will to 0.12, so it is little more than the filler wire, and that's how the A number differs from the filler wire or from the parent metal. And therefore the three numbers are very important for us: the P number, F number, and A number. Now, once we understand that this is going to be a different, we also see that the fluidity of the molten metal, which is also a factor for A numbers to separate it out, or there are certain alloys which are sluggish, and they are sluggish because of the diffusion kinetics, how the parent metal and the weld metal are going to really adhere to each other, and that depends upon the sluggishness or the viscosity or the fluidity of the metal. The surface tension of the material improves and the material flows if the viscosity is low, fluidity is high, and the kinetics or the dynamics of the liquid alloy or the fusion kinetics is surely going to improve upon it and has a better fusion. Now, looking at the earlier slide of the various types and understanding of this filler metal, let's go to the next slide where we'll be talking about positioning of layers and passes. The positioning of layers and passes is, as you see here in the first center, this one, that we have a hot pass, the root run as we call, and then we have the fill passes, and after the number of fill passes we have the capping or the covering layer. So that is also described here, and as we see on the visual, the internally, if you see this, you see clearly two lines. One is the fusion line, another one is the penetration line. Like in earlier slide we saw that there is a dilution which is coming. So similarly, a dilution happens between the layers and between the passes also. So every pass may have a different chemistry, every layer may have a different chemistry based on how much dilution we are permitting. If the dilution is going to be less than 10%, it will not create much of an impact, but if the dilution levels are higher, then it will have an impact on every layer, and that is where we need to ensure that we position these layers very well from the metallurgical point of view and also from the non-destructive testing point of view, because based on this positioning of these layers we will be having what is the resultant gap, and that we will be seeing it in our next slide. But see here the type of joints. For a butt joint we have 1, 2, 3, 4, 5, 6, 7 layers have been done here. Now if you are depositing 1 and 2, your original edge preparation you started with is almost intact. However, the profile of this first shall not be very concave or convex, should be as flat as possible so that the layer 2 can be deposited very well without having any imperfections at these corners. If it is too convex, then this the edge preparation is going to be really difficult, and that is where we are going to go back and really see how we are going to deposit these runs so that the fusion on both ends is going to be good, and also we will be having a good amount of fillet joints for the getting the throat and the leg lengths. So normally in our WPS we just write down this number of layers. What I want is really if you can make for the number of passes and the layers, if we can specify what are the current voltage we are able to give, and also if we can give what should be the minimum gap between each layer and a pass. If we are able to do that, like here we have given example that for a 1.2 dia wire, if we can keep 2 to 2.5 millimeter gap and a proper angle, then like we maintain root gap, root face, weld edge preparation for every layer, it shall be for every pass also, and that will give a sound weld which will have a good fusion, which will have a good metallurgical characteristics. The dilution levels can be also maintained. The heat input, as you see here, is varying in different this one, especially in the single V joints. It is becomes very difficult because one side is almost square, it's square, and the other side is having an angle, and you have to have accessibility to ensure that this vertical edge is also fusing whereas the inclined edge is also fusing, and inter between the layers, that is between